Renewable energy conversions. Welcome to Lecture 18 of Module 4, Manufacturing Processes, Energy Conversions, and Mechanical Automation. In the previous lecture, we studied non-renewable energy conversions, including fossil fuel-based power generation and nuclear energy. In this lecture, we will focus on renewable energy conversions. We will understand how naturally replenished energy sources such as water, wind, and sunlight can be converted into useful electrical or thermal energy. We will also study biomass energy and fuel cells. Let us begin by understanding the different types of energy resources. Next slide. Energy resources. Energy resources can broadly be classified into non-renewable and renewable sources. Non-renewable sources include coal, oil, natural gas, and nuclear fuels. These resources are available in limited quantities and are not replenished on a human timescale. On the other hand, renewable sources are naturally replenished. Examples shown on this slide include the sun, wind, and hydroelectric power. The important difference is that renewable energy sources can be continuously replenished through natural processes. In this lecture, we will concentrate on how these renewable resources are converted into useful forms of energy. Next slide. Sustainable and renewable energy technologies. Renewable energy is closely connected with the concept of sustainability. Sustainable and renewable energy technologies aim to reduce environmental impact, decrease dependency on fossil fuels, and ensure long-term energy availability. The slide identifies several important renewable energy technologies. They include wind energy, solar energy, hydropower, biomass, and bioenergy, geothermal energy. The slide also gives criteria for sustainable energy technologies. They should have low or zero greenhouse gas emissions, cause minimal environmental degradation, use land and water efficiently, and provide safety and long-term viability. Therefore, renewable energy is not simply about replacing fossil fuels. It is also about producing energy in a way that can be sustained over a long period. Next slide. Tidal power. Let us begin with tidal power or hydroelectric power. Hydroelectric power uses the energy stored in water. The basic energy conversion shown on this slide is potential energy of water to kinetic energy of turbine to electrical energy using generator. Water stored at a height possesses potential energy. When the water is allowed to flow downward, this potential energy is converted into kinetic energy. The flowing water strikes or passes through the turbine and causes it to rotate. The rotating turbine drives an electrical generator. The generator then converts the mechanical energy into electrical energy. Tidal power is presented here as a renewable and economical energy resource with low operating and maintenance costs. The slide also highlights additional benefits such as flood control, irrigation, fishery, and recreation. Next slide. Layout of hydroelectric power plant. This slide shows the layout of a hydroelectric power plant. Let us follow the flow of water. Water is stored in the reservoir behind the dam. The stored water has potential energy because of its elevation. When the gate is opened, water flows through the pressure tunnel and penstock. A surge tank is provided in the water passage, and the water finally reaches the turbine through the inlet valve. The flowing water rotates the hydraulic turbine. The turbine shaft is connected to an electric generator. The generator produces electrical energy. The electrical output then passes through a transformer before being transmitted through power lines. After passing through the turbine, the water is discharged through the draft tube into the tailwater region. So the complete conversion is stored water to flowing water to turbine rotation to generator to electrical energy. Next slide. Types of hydroelectric power plants. Hydroelectric power plants can be classified according to the head of water. The slide identifies three categories. For high head power plants, the turbine used is the Pelton wheel. For medium head power plants, the commonly indicated turbine is the Francis turbine. For low head power plants, the turbine used is the Kaplan turbine. The graph on this slide illustrates how these turbines are associated with different ranges of head and specific speed. So, a simple way to remember this classification is high head, Pelton medium head, Francis low head, Kaplan. The selection of the turbine depends mainly on the available water head and operating conditions. Next slide. Wind energy, wind turbine or aerogenerator. Now let us move to wind energy conversion. A useful way to understand a wind turbine is to think of an electric motor working in reverse. An electric motor receives electrical energy and produces mechanical rotation. A wind turbine does the reverse. It receives the kinetic energy of moving air and converts it into rotational energy. The blades of the wind turbine capture the kinetic energy of the wind. This causes the rotor to rotate. The rotational energy is then transmitted through gears where necessary to increase the speed suitable for driving the generator. Therefore, the energy conversion is wind kinetic energy to rotational energy to electrical energy. Next slide. Horizontal axis wind power generator. This slide shows a horizontal axis wind power generator. The wind flows toward the rotor blades. The blades capture the kinetic energy of the wind and rotate the rotor shaft. The shaft is connected to a gearbox. The gearbox increases the rotational speed before transmitting it to the electrical generator. The generator converts the mechanical rotational energy into electrical energy. The electrical output passes through switchgear and is then supplied to the power transmission system. The diagram also shows a wind speed and direction indicator which helps determine the prevailing wind conditions. So, the energy conversion sequence is wind flow to rotor and gearbox to electric generator to electrical energy. Next slide. Solar energy. Solar photovoltaic systems. Now let us look at solar photovoltaic or PV systems. A solar PV system converts sunlight directly into electricity using solar panels. Let us understand what happens inside the solar cell. Sunlight falls on the solar panel. The photons in sunlight interact with the silicon cells. The photon energy is transferred to electrons. These electrons become free to move. The electric field inside the solar cell pushes the electrons toward the appropriate layer. The electrons then flow through an external circuit. This produces direct current or DC electricity. The DC electricity can then be supplied to an inverter. The inverter converts DC into AC electricity, which can be used by homes, businesses, or other electrical loads. So, the basic conversion is sunlight to electrical energy in DC form to inverter to AC electricity. Next slide. Solar photovoltaic system. This slide presents a simple practical arrangement of a solar PV system. Sunlight falls on the solar panel. The solar panel produces electrical energy in the form of DC. This DC output is connected to an inverter. The inverter converts the DC electricity into AC electricity. The AC electricity can then supply an electrical load or be connected to the electrical grid. Therefore, the basic flow shown here is sunlight to solar panel to inverter to AC load / grid. The important point is that, unlike a thermal power plant, a photovoltaic system does not first produce steam or mechanical rotation. It converts solar radiation directly into electrical energy. Next slide. Concentrated solar power. Another method of using solar energy is concentrated solar power or CSP. Unlike a photovoltaic system, CSP does not directly convert sunlight into electricity. Instead, mirrors are used to concentrate sunlight onto a receiver. The concentrated sunlight heats a working fluid. The slide gives examples of working fluids such as molten salt, oil, or steam. The heated fluid transfers thermal energy to a heat exchanger. The heat exchanger produces high pressure steam. The steam drives a turbine. The turbine rotates an electrical generator. The generator produces AC electricity which can be supplied to the grid or used on site. So, the energy conversion is solar radiation to thermal energy, to steam energy, to turbine mechanical energy, to electrical energy. This is quite different from solar PV, which converts sunlight directly into electricity. Next slide. Concentrated solar power. This slide gives a simple visual representation of CSP. The diagram shows parabolic trough mirrors concentrating sunlight. The concentrated solar energy is transferred to a heat exchanger. The heat exchanger produces the thermal conditions needed to generate steam. The steam drives a steam turbine. The turbine is connected to an electrical generation system, and the electricity is supplied to the grid. The important thing to remember is that CSP uses the sun essentially as a heat source. Therefore, its energy conversion resembles a conventional thermal power plant, except that the heat comes from concentrated solar radiation rather than combustion of fossil fuel. Next slide. Solar thermal systems. Now we come to solar thermal systems. A solar thermal system captures sunlight and uses it to heat water or air for residential or industrial applications. Let us follow the process. First, sunlight falls on the solar collectors, which are typically installed on a roof. The collector absorbs solar radiation and transfers the heat to a fluid. The heated fluid circulates through pipes. The heat is then transferred to a storage tank, particularly in applications such as water heating. After giving up its heat, the fluid cools down and returns to the collector. The cycle then repeats. So the basic conversion is solar radiation to thermal energy to heated fluid to useful heat. Unlike solar PV, the main output here is heat rather than electricity. Next slide. Biomass energy. Biomass power plant. Now let us study biomass power plants. Biomass power plants burn organic materials such as wood and crop waste to generate electricity or heat. The slide emphasizes that biomass uses renewable organic material instead of coal or gas. Biomass is considered renewable when it is sourced, harvested, and regrown sustainably. Let us follow the energy conversion process. First, biomass acts as the fuel. The biomass is burned in a boiler to produce heat. The heat converts water into steam. The steam drives a turbine. The turbine produces mechanical motion. The turbine drives a generator, which converts the mechanical energy into electricity. Finally, the used steam enters the condenser, where it is converted back into water. So, the energy conversion is biomass chemical energy to heat energy to steam energy to mechanical energy to electrical energy. In this way, biomass can provide electricity using a conversion process similar to a conventional steam power plant, but with renewable organic fuel. Next slide. Fuel cells. Difference from a battery. The final part of the lecture introduces fuel cells. To understand a fuel cell, the slide first compares it with a battery. A battery stores its chemical reactants internally. It converts those stored chemicals into electricity. Because the chemicals inside a battery are eventually consumed, the battery eventually goes dead and must either be recharged or replaced. A fuel cell works differently. The reactants are supplied externally. The diagram compares a hydrogen fuel cell with a galvanic cell or battery. The fuel cell is represented as an open system because hydrogen and oxygen are continuously supplied. The battery is represented as a closed system because its reactants are stored internally. Therefore, a fuel cell can continue generating electricity as long as the required reactants are supplied. Next slide. How does a fuel cell work? Let us now understand the working of a hydrogen fuel cell. Hydrogen fuel is supplied to the anode. At the anode, hydrogen reacts with a catalyst. This produces positively charged particles and releases electrons. The positively charged particles move through the electrolyte. The electrons cannot pass directly through the electrolyte. Instead, they travel through an external electrical circuit. This movement of electrons produces electrical current. Finally, at the cathode, the particles and electrons react with oxygen. The reaction produces water and usable heat. So the basic process is hydrogen plus oxygen yields electricity plus water plus heat. The important feature is that the fuel cell converts chemical energy into electrical energy through an electrochemical reaction rather than through combustion followed by mechanical rotation. Next slide. Commercial fuel cell use. This final slide shows examples of commercial applications of fuel cells. Fuel cells can convert hydrogen into electricity for powering vehicles and equipment. The slide highlights applications such as public transportation, commercial trucks, long-haul logistics, material handling equipment, airport and ground support, marine and port operations. The example shown is a fuel cell powered commercial vehicle. The slide highlights characteristics such as zero emissions at the point of use, long range, fast refueling, reliability, and efficiency. Therefore, fuel cells have potential applications, particularly where continuous operation, long range, and relatively fast refueling are important. This brings us to the end of Lecture 18, Renewable Energy Conversions. We have studied the conversion of energy from water, wind, sunlight, biomass, and hydrogen into useful electrical or thermal energy. The key idea throughout this lecture is that different renewable resources require different conversion technologies. Thank you.